Hello! This will be a demonstration of Proposition 19 from Book 6 of Euclid's Elements, which says that similar triangles are to one another in duplicate ratio of their corresponding sides. What that's going to look like is we're going to have two triangles, A, B, C. That, A, B, C. And some similar triangle, D, E, F. D, E, F. And because they're similar, we know that the angle DEF is going to be equal to the angle ABC, and that AB is to BC just as DE is to EF. And what we're going to prove, given this, is that the triangle ABC is to the triangle DEF, just as the duplicate of BC to EC. Well, we're going to begin by making the straight line BG, which is a third proportional to BC and EF. We can do this by Proposition 611. So we're going to cut off BG, something like that, so that BC is to EF, just as EF is to BG. Now we're going to join the straight line AG by postulate 1. Now, having been given that AB is to BC, just as DE is to EF, by Proposition 516, we can alternate this proportion and say that AB is to DF, just as BC is to EF, but BC is to EF, just as EF is to BG, and so by 511 we have two ratios which are the same ratio, which means they are the same with one another, so that AB is to DE, just as EF is to BG. Which then means that between the two triangles ABG and DEF, we have one angle equal to one angle, and the sides about the angle reciprocally proportional. Again, the way to identify this is that we have two sides from the same triangle DEF next to each other in the proportion, so that's how we can identify reciprocal proportionality. So knowing that the angle ABG is equal to the angle DEF, we were given that, and that AB is to DE, just as EF is to BG, we have just found that. We can then say by Proposition 615 that the two triangles ABG and DEF are equal to each other. They have one angle equal to one angle, and the sides about the equal angle is reciprocally proportional, so 615 tells us that the two triangles ABG and DEF are equal to each other. Now, going back to this original proportion, or not exactly original, but with BG, we made BG such that BC is to EF, just as EF is to BG, which means we have three magnitudes which are proportional, which means by the 9th definition of Book 5, which is the definition of duplicate ratio, CB has to BG a duplicate ratio that CB has to EF. But CB is to BG, just as the triangle ABC is to the triangle ABG. So BC is to BG, just as the triangle ABC is to the triangle ABG. Because of Proposition 6.1, these two triangles ABG and ABC are under equal height, or under the same height, so they are to each other as their bases. So CB is to BG, just as the triangle ABC is to the triangle ABG. But CB is to BG in duplicate ratio to CB and EF, which means by 511 we have two ratios which are the same with the same ratio, which means they are the same with one another, which means that the triangle ABC is to the triangle ABG, just as the duplicate ratio of CB to EF. But the triangle ABG was found to be equal to the triangle DEF. We found that in the third step up here, which means we can substitute it in by a property of magnitudes and say that the triangle ABC is also to the triangle DEF in duplicate ratio that BC is to EF. And this being what we set out to prove, we are done with the proposition, therefore, etc. QED. Now there is a porism appended to this proposition that says that if three straight lines be proportional, the first straight line is to the third straight line, just as the figure on the first is to the similar figure on the second. How we discover that is we have this proportion here that BC is to EF, just as EF is to BG. And we found that BC is to BG, the first is to the third, just as the triangle on the first, which is ABC, is to the triangle on the second, which is the triangle DEF. So that's how we have that if three straight lines are proportional, the first is to the third straight line, just as the figure on the first is to the similarly described figure on the second. Admittedly, and this is something that Heath agrees with, this porism is misplaced. It is properly appended to proposition 620, which is the one after this. But, you know, what can you do? This porism is true, so I'm going to continue referring to it as the porism of 619, even though it admittedly is a little misplaced. Before I end the video, I want to explain a little bit about what exactly duplicate ratio is and how we might understand this porism in a modern notation. An example of a duplicate ratio would be if we have, so let's say we have three numbers. Numbers aren't magnitudes, but work with me for a little bit. We know that 4 is to 6, just as 6 is to 9, right? And the ratio is obviously 2 to 3, right? 4 is to 6, just as 2 is to 3. And so we would say that 4 to 9 is the duplicate of the ratio 4 to 6, or in other words, that 4 is to 9 in duplicate ratio that 2 is to 3. Now, we can understand this by taking the ratio 2 to 3, and what we do with this is that we actually square this, right? Because if you take a fraction and you square it, you just square the numerator over the square of the denominator. So 2 to 3 squared is just going to be 4 to 9, and look at that. The duplicate ratio is 4 to 9, given this three-term proportion. So what this means for the porism is, again, an understanding that we saw in book 2, that squares are areas. And so how you can understand this porism is that the first straight line is to the third, 4 is to 9, just as the square of 4 is to the square of 6. But you can actually represent all areas as squared. So this applies to like if the areas be triangles or parallelograms or circles, even for that matter. Because this process of this arithmetical process of squaring is equivalent to a geometric area, this is how we would understand this porism. That 4 is to 9, just as the square on 2, 2 squared, is to the square on 3, 3 squared. I hope that helps understanding duplicate ratio. This is going to come back in proposition 623 when Euclid talks about compound ratio. It becomes very important then. So, look forward to that. I've got nothing else to say about this proposition, so I'll end the video here and move on to 620.